So good. All right. I think we are a couple of minutes past, so I might start introducing things a little bit. I know some people will probably still join in, but that's fine. They won't be bored by my introduction. So welcome all of you to this ISPA. Okay. Yes. I'll talk about that in a moment. That's true. So welcome to all of you to this ISPA webinar organized by Bayesian Analysis. Today, we are fortunate to have a really interesting paper to discuss. It's called Deep Gaussian Processes for Calibration of Computer Models. And in fact, there's even Bayesian added on the title here, which I didn't have on my slides, but that's perfect. The authors are both based in French institutions, Sébastien Marmin and Maurizio Filippone. Sébastien is in the French National Metrology Institute. He obtained his PhD from the Institute of Mathematical Statistics at the University of Bern, and did a stint as a research assistant in the machine learning group of EURECOM with the second author, Maurizio Filippone. Maurizio is the AXA Chair of Computational Statistics at EURECOM, which is a graduate school of and a research center in digital sciences located in the French Riviera, I am led to believe, which must be a very nice location indeed. So Sébastien and Maurizio will present their paper. In fact, I think Sébastien will present the main paper and Maurizio will present the rejoinder afterwards. And then this paper, by the way, has just appeared in Bayesian Analysis in the December issue. If you have any questions during the seminar, please feel free to put them in the Q&A section so we can see the panel can see them. After the presentation of the main paper, we have insightful discussions, 3 discussions. The first one will be by Dave Higdon and Stephen Walsh, the second one by Tony O'Hagan, and the third one by Annie Sauer and Bobby Gramacy. Now, after the discussants, so Maurizio will present a brief rejoinder. If we have any time left, we will allow for other participants to ask questions or engage in discussion or give comments if you want. Please use the Q&A section for that, and maybe if we have a few minutes, we can allow for people to sort of raise their hands and speak if they want to, of course. Now, finally, I want to make everybody aware that this is being recorded, and this will be at some point streamed. It is also going to be an ISBA resource, so there will be a link to it that will be available to certainly will be known if you want to people on the ISBA mailing list. Okay. All right. So without further ado, can I ask Sébastien to start the presentation, which hopefully in about 40 minutes or so, he will be able to sort of tell us a lot about the actual paper. So, Sébastien, please.
Thank you, Mark, and thanks to everybody who allowed to have this nice webinar. So, deep Gaussian process for Bayesian calibration of computer models. I start with a bit of context. So, the goal is to have inference for parameter of expensive computer codes from data. And in particular, these parameters have interpretation of physical quantities that cannot observe directly. I will come in a minute about this. And it's a calibration of computer models have applications in many topics like elemental sciences, biology, and mechanical engineering, to name a few. So there are 2 main objectives: how to estimate the parameters of the computer code that try to approximate a natural phenomenon, and how to make predictions, how to combine the computer code outputs and the real measurements. So there are 2 objectives, and sometimes they are not going in the same direction. They are a bit antagonist. So to start seeing progressively, I will start with Gaussian process modeling. So when we want to have a model on an unknown function that we know only on few points, and the observation points are typically expensive. What is often done in a Bayesian manner is to assume that our unknown function is a random sample path from a Gaussian process, so a random function generator. Here, it's noted y. So our unknown function is one of these orange curve, and it's our prior belief before having observation points. And there is a nice way to compute the posterior with analytical formulas to have a posterior over our unknown function when we know few data points. So this framework is well known and provide some quantification of uncertainty. We see here the deciles and also posterior sample path that can provide uncertainty. And we can also inject prior knowledge on F, for example, the regularity, or if there's some symmetry in the unknown function that we want to inject in the modeling. So what have been done is using these Gaussian process models in Kennedy and O'Hagan in 2001 to make calibration. So now I will go more precisely about the Bayesian calibration model that we will explore today. So as I said, we have a natural phenomenon, F, and a computer code that try to reproduce the natural phenomenon. And the computer code is not perfect, so there is a discrepancy between the two. And we have different type of input. We have the input variable x. It's an input variable where we control the location in the table. It can be a location where we do the samples. And we have a calibration parameter that, in this case, we don't control where we measure. We actually want to know it. It's an unknown. It can be a physical constant, for example. So this is one part of the problem is first to make prediction and also to estimate this input, this calibration parameter, theta here. And the computer code has the same type of inputs, but of course, for the computer code, we control the location in the input space. So we name them differently, x star and t. So it's the same notation as in the paper, as in the original paper. And for output, we have z that try to approximate y. So we see here the output of eta has a sum with the output of delta, the discrepancy, to give y. And there are a few issues that were already noticed early, is that GPs cannot scale good when we start to have a lot of data. So and also there is no analytical formula for the posterior of the whole model. So we are forced to use MCMC inference, and it can be sometimes difficult to tune or a bit slow to converge. And also recently there is more and more research done about deep learning, and that the deep architecture can be a way to have more flexibility with a given number of parameters. So GP models doesn't benefit from a deep architecture. So this is a bit the target of the paper. We aim at extend the capabilities of the GPs in calibration using DGPs, so deep Gaussian process. So a deep Gaussian process is not really a Gaussian process, it's just a composition of Gaussian process. So if we have Y1, Y2, Y3, if they are GPs, so random functions, their composition is named a deep GP. And a second target is to have a more flexible framework, especially for the discrepancy that is additive in the original paper, and we want to have more flexibility and be more general than just having an additive discrepancy. And the third objective is to obtain a scalable framework, in particular using variational inference combined with random feature approximation. So here is a toy example where I already show what we obtain on this toy example. So on the top left, we have the probability distribution of what we look for, the calibration parameter, theta. We have in black the prior, and in green the posterior, the true posterior. And what our method gives us is the blue line as a posterior. So we see it's close enough to the true posterior, it's close enough to the true value, the red line, but it's not exactly the true posterior. And I want to tell here, what we will obtain is an approximation of the posterior. It's a compromise with also scalability and computation time. On the top right panel, we have our physical phenomenon. So it's a assume we have a physical phenomenon with two inputs, x and theta. Theta, we don't know it. And at the bottom, we have our Gaussian process approximation of the real phenomenon. So we see the Gaussian process with only few points is able to approximate good the real physical phenomenon. And this will be our computer code. And here for this example, the discrepancy is only a white noise, a small white noise. And on the bottom right, on the bottom left, sorry, we have the input space, so theta and x. X is the input variable, theta is the calibration parameter. And we show in the grayscale, we show sorry. In grayscale, we saw the true posterior. So again, the red line with the true value of theta is in the true posterior. And in colors, we have the data. So we have two types of data, as I said. We have the computer runs. So the color is the Z scale, so the color scale of the right panels. So we have two types of data. We have the computer runs, for which we control the position both in the input variable and also in the calibration parameter. So this is why it's points. And we have also the real world observations. So the observations, not the computer runs, just the observations, where of course we don't know theta because it's the whole point of calibration. And the goal of the model is to find which value of theta there is a match between the colors, between the computer runs and the real world observation. And what the model tells us here is that, yeah, the theta cannot be here because there is a mismatch of color between the real world observation in green and in red and the computer run in green. We really observe that the theta should be here, where there is an agreement between the computer runs and the real world observation, the lines, because here they are both red. We could also be here, for example, where there is also an agreement. But what the model is able to show is that we here the green is between the blue and the yellow, so he's really able to recognize that there's a higher probability that the real calibration parameter is in this space. So in what follow is basically doing this, but in higher dimension and with real data. And also we will come to the technique we employed. And important aspect of our paper is random Fourier features. So I will, so it's not something new, but I will spend some time explaining what is random Fourier features. So we have a covariance function, and the covariance function gives us sample path, so random function. So here we have random function in 2 dimensions, and I can show you different sample path. So here on the top is the exact covariance and the exact sample path we target. And random Fourier features, what the first step is to sample in the spectrum. So in the Fourier transform of the covariance, we sample according to the density of the spectrum, one features, and this will give us a direction for a sine wave. And this is what we see on the bottom. We have a sine wave that will approximate the exact covariance. So we see here the approximation is bad because we only have one random features, but we are able to have random functions. So now if we sample two random features in the spectrum, we see that with only 2 degrees of freedom, we already have in the sample path better the sample path have an infinity of degree of freedom, and on the bottom only 5. And we see that for the prior, it doesn't change much. This is the prior. And for 20 random features, we see that the sample paths are hard to distinguish. I would give you a sample path on the top, and you couldn't tell me if the sample path will be with 20 degrees of freedom or with an infinity degree of freedom. This works, of course, because we are only in dimension 2, and it's quite regular. The covariance is quite regular. But it's to show how random features are good in some specific case to approximate a prior. So the equation of this behind this is quite simple. We replace a Gaussian process by a Bayesian linear model, which is also a Gaussian process. And here's the equation. Our approximate Gaussian process is a linear combination of sine and cosinus waves with well-chosen frequencies and with IID weights. Simply this. And it's easy to show that when the number of random features increase to infinity, our approximation is totally accurate. Like in distribution, there is a convergence in distribution. And when we compute the posterior, everything is Gaussian, and we can compute by optimization or just inverting a matrix when there's not too much data. What is important to note is in the following, we will have this perspective that we actually, this equation can be seen as one layer of a neural network because we just apply one linear transformation on X then we apply a nonlinear function, and then we again apply a linear transformation. So it's exactly in the framework of a Bayesian neural network. And this is the main image of the paper. Is this is we replace all the Gaussian process by their formulation as a neural network approximation. And we see that we have two neural networks, one for the natural phenomenon and one for the computer code, but they evolve together. They have the same weights for partly because they share eta, the computer model. They share the shared computer model, but they have different inputs. They have the same weights, but different inputs. And here we have a sum. And I will discuss a bit later that we don't have to have a sum here because we can also use another Gaussian process. We will generalize this. And of course, this is only one layer, but we can also generalize to several layers to have more flexibility in the models. So now the question is, how do we train this with keeping a sense of uncertainty quantification? So as I said, we could, if there is only one layer, the best is, and not so much data, the best is just to invert a matrix or just use Gaussian process. But the question is when we have more data. So if we forget a bit the calibration and we just give us some input points and some output values, labels, and we give us some parameter to estimate with the likelihood and the prior distribution on theta, the parameters we want to estimate. The question is, how do we estimate how do we estimate theta? So stochastic variational inference offer to choose a family of possible posterior, a calligraphical Q, and we try to minimize the candidate posterior, the distance between the candidate posterior and the true posterior. So of course we cannot compute the true posterior, but the main point of variational inference is that this minimization of distance is equivalent to the maximization of a lower bound of the log marginal likelihood. It's what is written here. If we look at the expectation over the candidate posterior of the log of the likelihood minus the KL divergence between the candidate posterior and the prior, this will be our loss function. And this second term, the first term is a fitting term, and the second term is a regularization term. One important part in variational inference is the question the trade-off between how much budget we want to invest in the optimization and also the quality of the approximation. And in our paper, we decided to use multivariate normal distribution, so quite a very narrow family, in particular without correlation. So in our code, it's easy to implement also the correlation, but we didn't have the use in the experiments. And another constraint on the family of candidates is also that the divergence should be easy to compute, and this basically means that the divergence should be analytical. So there's not a lot of so this is a drawback of variational inference, is there is not a lot of choice in the family of posterior candidates. So now we had to adapt this to Bayesian calibration. In particular, the question was how to deal with a lot of data, and in what is often done is mini batch. So we adapted mini batch for the Bayesian calibration. So in particular, when the number of real-world observation is usually small compared to the number of computer runs, so we had to ensure that that when we perform mini batch and subsampling of the data, we always have enough data points of real-world observations. So the fitting term here. So this time the parameters are the weights of the computer model, the weights of the discrepancy, and of course theta, the parameters of the calibration parameter. And the fitting term is not we used to have a V, so the labels, and now we have two types of labels: the computer runs and the real-world observation, Y and Z. And we perform a Monte Carlo estimation of this term with NMC samples, and assuming independence, we can have a sum of log of density, and to ensure that we have an unbiased estimate, we have this ratio on n over m. So this is how we compute the fitting term in variational inference. So now we applied this method on several cases taken from the literature. One case was an application in cell biology, where we have one input variable, 3 calibration parameters, 19 observation, and 300 computer runs. We compare with several methods from the literature, and what we see. So our method is named DGP cal additive and DGP cal general. I will come back to this. So we have two versions of our model. One is with additive discrepancy, and another one is with general discrepancy, so a more general discrepancy. And we see that we are very fast and we perform good prediction. So and we also have a good posterior of the prediction. So the generalization of the calibration model using DGP, we proposed in the paper to write the natural phenomenon as a composition of the computer model and the input variable. So it's a more general, of course, because if we replace this warping gamma by identity for the first variable plus a Gaussian process of the second variable, we would boil down to the original model, But now we have a more general model where we assume a GP prior on the warping. And we also, as I said, generalize the model by not considering only GPs, but deep GPs, and considering a deep GP prior for eta and a deep GP prior for the warping or for the discrepancy when the discrepancy is additive. So deep GP are particularly useful when the emulator or the real process exhibit a space-dependent behavior. And it's difficult to model with Gaussian process, even if it's possible with non-stationary Gaussian process. Often the non-stationary Gaussian process has to be designed before seeing the data. And here, in this case, the non-stationarities are learned from the data using deep GPs. So it's particularly appealing in some challenging application. And also, its deep GP are not easily inferred because, of course, there's a lot of degree of freedom to infer. But with the random features, the scalability is feasible. So another example is with a real-world data. So radionuclide diffusion into aquifers, also taken from the literature, where we have non-smooth data and input space of 8 dimensions with 2 calibration parameter, 2 input variable and six calibration parameters. We have about 18,000 computer runs and only 10 observations. So we will come back to this, but there's definitely a problem with identifiability when the calibration space is so big in the dimension, and also when there's few real observations. And in this experiment, we see that our shallow model, where we will have only one layer, the prediction is bad compared to when we use several 2 layers. So deep is 2 layers is already considered deep, and here we have a better prediction. And we made a third experiment. This one we wanted to push the capability in the scalabilities of number of data. So we again have 8 dimensions, but this time we have 1 million computer runs and 100,000 observations, and with 50 random features. We infer with 50 random features and only shallow Gaussian process. And only the method sum of trees could perform inference, and also our model. And we see that we are much faster, and we have also more able to have a better prediction. And especially for the calibration, we see that we are able to, I forgot to say, this is synthetic data. So we know perfectly where is the theta. So the true theta is in black. So we are able to retrieve the true theta. We see that in blue, so our model is in blue. We see that we are not super confident with our prediction. We see that the variance is quite large, but we are still able, if we look at the means, we're still able to retrieve the true values, and not being confident is maybe good sometimes. And also, yeah, the sum of tree method couldn't find the true values. Okay. So I don't know what is the time now. Maybe I was Mark.
Looks good.
Looks good. Yeah. So yeah, to say as a conclusion, I want to say that we bring new advancements, some of new advancements in the Gaussian process literature to the field of computer model and calibration in particular. So in this paper, we proposed Deep GP Cal, which offers a number of improvements over the classical framework of Kennedy and O'Hagan in 2001 to tackle the calibration problems where quantification of uncertainty is of primary interest. And from the modeling perspective, we cast this classical model as a special case of a more general model, both for the deep aspect, replacing Gaussian process by deep Gaussian process, and also by generalizing the discrepancy as a warped version of the emulator of the computer model. One thing to add is this approximation is very well suited for simple implementation with modern tools in machine learning, like automatic differentiation, and is very well suited also for GPU type hardware. In a perspective, we want to explore more experimental design aspects, especially when it happens often when you talk with practitioners that the budget for having a real world experiments doesn't come all at once, but progressively. So once you already have a first model, you want to find the best location for the next experiments. And this is typically important for the practitioners, that with a very few amount of data, you optimize the knowledge. And there's a lot to be done in this field. In particular, in the paper, we discuss a bit about how to sequentially reduce the posterior variance of the calibration parameter. And we also discussed in the paper the issue of identifiability. So to be clear, it's the identifiability is when the same data is not enough. A given data is not enough to locate the true value of theta, because the parameter space, the calibration space, is so big that there are many calibration parameters that can explain the data. And there's a way to do this, but there's always this compromise that if you reduce too much the flexibility, then you introduce a bias. So we want to insist. I mean, it's often the case in Bayesian work, the importance of prior. In particular, I wanted to say that but especially here, because the prior can help mitigate the issue of the lack of identifiability. And also looking at the data can dictate choice for the prior, for instance, choosing a GP or a deep GP when we see, for example, here the case with the radionuclide diffusion test case. And also, it's a bit obvious, but we insist also that when we have multiple inputs, this can help a lot for the identifiability and to locate, because there is more constraint on the calibration parameter. And we discuss also at the end of the paper the links that I think is not explored enough between this disentanglement in Variational autoencoder. There's a latent space that have also similar question as identifiability in calibration, and we should also explore in this direction. So the latent space in a variational autoencoder has also a problem with the identifiability. So I stop here. Thanks a lot for the time, and I'm ready for questions and all remarks. Yeah.
Wonderful. Thank you very much, Sébastien, for a very well-timed presentation. That's great. There are a few questions, but and I think Maurizio is actually typing an answer to one of them, which is great.
Great.
think the other question I can see is basically somebody asking, would it be possible to apply a wavelet transform instead of a Fourier transform in expressing the covariance in the first part of your paper? If you have a 30-second answer to that.
It got me very curious about what happened if you do this. I actually study a bit wavelets with GPs. The problem with wavelet with GPs is often it needs a very low dimension to work. I mean, when wavelet over 3 or 4 dimension, it's not wavelets anymore. It's you cannot have real wavelets. But it was a try. I mean, I don't know why exactly it would be interesting, but it's yeah, it's a good question.
Okay, excellent. Well, thank you very much. So I think we're down to the discussions now, and as promised, I think Dave and Steve would be the first one up. So Dave, do you have any slides to present?
Yeah, I will try to share my screen right now.
Okay, wonderful.
All right, how is that? Something visible for everyone?
We still see the references. Now it comes. Yes, that's it. Wonderful. Thank you.
Excellent. All right, so this discussion is with Steve Walsh, who is also at Virginia Tech, graduating hopefully next semester. So I just want to say thanks to the authors. I think the paper was very interesting and lots of sort of new ideas and fresh concepts into this world of computer model calibration, emulation, and inference with computational models. So I think that's great. With our limited time here, I thought I might just sort of talk real quickly about the 3 sort of points in black here, but I've got other ones in gray as well. So we can think about those or answer questions about those. And don't worry about the slides here. I'm really only going to have 4 slides here. But one of the advances here, I think, is the use of a deep GP rather than a GP for the emulator. And I know, like, I worked on some of that BART or Bayesian additive trees emulator as well, and that was not as successful as we had hoped. But the deep GP does some things that the usual GP or lots of additive model functions just don't do all that well, and this shows up in this Aquaphor, this diffusion of radionuclides problem. So this is sort of a more advanced version or a more complete version. I got this slide from a colleague on this one. But one of the measurements is this hydraulic head over time, and these are sort of long times here, right? Decades that we're talking about. But what happens is, some of these parameters like impermeability is going to control like when we see a change in the head over time. And so the change in the head might start earlier or later, depending on what these parameters might be. And these are shifts that aren't really real compatible with something like a Gaussian process or, additive tree models, because those sorts of models are good at getting us smooth changes in kind of this Y direction. But they're not really good at smooth changes in this in the location or where the phase is for these sorts of things. And what's nice about the deep GP is that it gives a rather natural way by looking at warping the space to say that, oh, now we have sort of a very smooth way that can be accounted for in the model where we have this shift of this plume or something happening over time that's shifting over time depending on a model parameter. So that's just one instance of where the warping that goes on in a deep GP I think is beneficial. We looked at other cases where it doesn't seem to do as well as a regular GP. So I think in certain settings it's doing better and others it isn't. And I think flow and porous media where different parameters change the arrival times of things is one where I think it is a good winner for that. And so I'm not surprised it did well in that case. So that was nice that they could apply that to that situation and really look like they're doing better in terms of the emulation. This is a slide I remember from, it must be a decade ago, maybe more, of looking at what are these challenges in statistics and computer model calibration and dealing with big data sets. But it's relevant here because I think this framework of embedding a deep GP within sort of a hierarchical Bayesian framework is a really nice concept that might have legs in other directions besides just computer model calibration. And so just to pick one thing here, I don't know if you can see my cursor very well. I didn't get the bonus jumbo size cursor, but on the left here is this ocean model, and it's at a pretty low resolution. And here it is at a much higher resolution. And of course, the problem is these higher resolution runs take, 10, 20, 100, thousands of times longer. So we can't do very many of these where we can do a lot more low resolution runs. And how do we combine these things in ways that are going to help us make inferences about reality, which is probably a lot closer to this high resolution run here. And so things like what goes on in high resolutions, you can see there's these pockets of very warm water moving out in directions that never happen in the low resolution run. And so if we're going to say, well, how do we build a connection to the high and the low resolutions? It's not, doing these additive sorts of things aren't the obvious way to go, but maybe these deep GPs, and certainly I have some references there on the side that people have looked at multi-resolution sorts of inferences, and deep GPs seem to have had some success there. Hard to say, it's early stages, but it's an encouraging way to be thinking about that, and that this paper made me think of that. Another kind of bridging of scales, which I think is harder, but I'll throw out there because why not? We got all these brains here. So if I look at these airplanes, we go from classical aerodynamics, where you have these very small parameterized models, to higher resolution, to full CFD sorts of models. You're bridging these scales here that are not naturally going to connect. And are there ways, when we talked about encoders and decoders and things like that, are there ways that live in this space of deep Gaussian processes, or embedding it in some other sort of hierarchical framework to connect these information from these different scales better? And sort of the one sort of real pressing one that goes on even today is this material science one, that we can have a very detailed look at the model, but we want to infer these very bulk properties like the stress-strain relationship of a very detailed specified piece of material. And so this is one that challenges out there that we're always trying to figure this sort of thing out, and it is a tough one. But maybe there's this idea that, again, this sort of deep GP encoder decoder kind of idea might be a way of linking bulk properties to very detailed material properties there. All right, and the last thing, just before I end it here, was this integration of lots of different experiments and lots of different simulation runs or simulation campaigns. And so here's again from my old history here. So this is maybe a 15-year-old sort of slide, but it's a one system that we could go from beginning to end, but it has lots of complex physical processes in between. And what we'd like to do is build up different types of experiments, small material experiments, experiments on equation state, maybe high explosive. There's more integrated experiments that aren't the full thing, but they just do, say, an implosion, and you see part of the system that you care about. You might see other ones that talk about the neutronics. But the idea is that we want to put all of these things together to try to make inferences about this whole system, or this whole system that's evolved over time. So what's happened over the last few decades? Almost all the parts have been swapped in with different types of materials, different sorts of things. And so no one really knows, or it's hard to make the argument about how is this thing going to behave? Or even if it falls off a shelf, what might happen then? So, so this idea of putting together lots of different small calibration problems to make one, large, massive one is one of the challenges that shows up. And here, maybe the codes are very similar all the way around, but in other setups, other computational settings, you might have a different computational model for the small scale experiments. You might have a different computational model for one type of integrated experiment. You might have a different one for these other types of integrated experiments. But here's a place where, again, this framework of how do we combine this stuff in a sensible way is going to be important. And the old historical way is, something like, oh, let's just product up the likelihoods and see what happens. And in those settings, it's always, the problem is we don't have, non-identifiability or too little uncertainty. We have, or too much uncertainty. We always have too little. That there's never enough uncertainty to go around when you're putting these things together. And so when we talk about things like worrying about non-identifiability and things like that. What do we need to do to solve it? All my perspective, all the things I've worked on always tell me like, oh, that is never the problem. Like you should just try to incorporate all the uncertainty you've got and live with it. And then in the next phase of your investigations, you're probably going to be sorry if you cut it down somehow artificially. So for instance, the material strength, and here we've got a line for some of those. The stress-strain relationship, the discrepancies are exactly doing the same thing as one of the parameters. But I don't want to say, oh, let's make the discrepancy 0. I want to account for the fact that, oh, this parameter, this stress-strain, this yield stress, might be really wide in my uncertainty space. And I usually want to take that along when I'm going up to a further downstream process because my prediction is going to depend on that. So so the ideas are incorporating the uncertainty seems to be a very important thing. And I would say don't rely too much on your prior to get this out that, oh, we're Bayesians. We're allowed to incorporate these trade-offs. That's part of our posterior. And in some cases, it makes sense to embrace that. So let me end it there and just say thanks again to the authors for us giving us an idea of a different way of kind of looking at this model calibration problem.
Right, wonderful. Thanks very much, Dave. So now Tony, I think, has no slides, so we don't. Yes.
Okay. Thank you, Mark. Thank you, Dave, and the authors. Well, first of all, I can begin with a few congratulations. The analysis of computer code outputs is obviously a topic I really care about. And my earliest contributions in this field date back more than 20 years. And enormous strides have been made since then by many contributors. And the authors of this paper have clearly made a major step forward. I confess, I know far too little about the technical aspects to be able to say anything constructive about them. But I am delighted to see this paper and deeply impressed by the work that's been going on. So first of all, a hearty congratulations to the authors for a fine paper. I was doing research in Bayesian methods before we had MCMC. And at that time, I never expected to ever do any practical applications. It was all theoretical stuff and far too difficult to compute. But since then, we've had massive progress in Bayesian methodology, and it's proceeded hand in hand with developments in computational tools. So this paper is a fine example of that kind of thing. The authors have given us powerful computational tools for the analysis of computer code outputs with model discrepancy. And we're not limited to using GPs. We can use deep GPs, which is also terribly wonderful. But in the work I did with Mark Kennedy and with Jenny Brynjarsdottir, we were not concerned about GPs or MCMC or any of that computational stuff. Mark and I were focused on showing the importance of model discrepancy. Jenny and I wanted to demonstrate the importance of prior information about model discrepancy. And I think, without being too unfair to the authors, I think we were developing statistical methodology, not computational methodology. I've never really been a computational guy. And so that's why a lot of this stuff passes way over my head. So whilst I truly welcome this paper, I'm afraid it doesn't actually help with the statistical questions that we were addressing at that time. So Jenny Brynjarsdottir and I tried to incorporate prior information about model discrepancy in really simple ways. We didn't even scratch the surface of this challenge. Formulating prior information about the discrepancy is hard, particularly now in the kind of model we're being proposed here, where we've got deep Gaussian processes and a general, possibly non-additive warping function, gamma. How are we going to input prior information about all of this? We had, in fact, in the original Kennedy and O'Hagan paper, we had not just an additive part, we had a multiplication as well. We had the true model is equal to discrepancy plus a multiplier of the computer code. So we were allowing some kind of scaling there in as well. So we were already doing a little bit more than has ever happened since, because everybody since seems to ignore that multiplier. But if you're going to go into this general warping functions, how on earth am I going to specify prior information about the discrepancy? Well, surely we could make progress. we could make progress in this whole area of formulating prior information about model discrepancy, even if we stick to simple Gaussian processes, additive models, or whatever. We could surely make more progress than has been made if as many people put as much effort into it as has been invested in computation. So here is my plea to all those listening to this webinar or reading this paper. Show how, in real applications, when I say real applications, I'm always awed by the kind of stuff that Dave Higdon's tackling. We're not talking about those kinds of applications. I couldn't even dream of that. But if we could take something real, something non-trivial, and show how to formulate prior information, genuine prior knowledge about model discrepancy, whether you're using Gaussian processes, deep Gaussian processes, or whatever, and then show the impact that this knowledge has on our inference about physical parameters. So many thanks to the authors, fascinating stuff, but just that little plea at the end. Can we do a little bit more statistics, please? Thank you.
Thank you very much, Tony. So now Annie, I think, will do the discussion that she wrote with Bobby Gramacy.
Yes, hi everyone. So I wrote my discussion with Bobby Gramacy. He's not able to be here, but I will talk for just a couple minutes on, I think one of the questions in the chat actually touches a little bit on the idea that we have kind of two parts of this work. There's the calibration framework, and then there's just the concept of a deep Gaussian process as a surrogate. So I wanted to talk a little bit about the kind of deep GP surrogate side of things. I only have 2 slides, so this will be pretty brief, but Sébastien touched on 2 of the important choices you have to make when you're doing a deep Gaussian process as your surrogate model. You have to do some kind of inferential approximation. So I have this called just the inferential apparatus. And because the posterior was this, functional composition of GPs is not generally tractable. So what a lot of people have chosen, and what Sébastien and Maurizio chose to do, is what we call approximate variational inference. And the alternative to that is, of course, some kind of MCMC framework. So there have been, as far as I know, 2 works on 2 different ways of doing MCMC. One is Hamiltonian Monte Carlo, and the other one, which I've worked on with Bobby and also a little bit with Dave, is elliptical slice sampling. And the question then becomes like, well, which one of these is better? Which are faster? When do they work better? But all of these are combined with some kind of computational apparatus to shortcut these cubic computational bottlenecks of, Gaussian process inference that I think most of us are familiar with. And some common choices for that is to do inducing points. That's been, I think, the norm in the deep GP literature for a while. I have recently worked on using Vecchia approximation, and then the current work that Sébastien talked about are these kind of random feature expansions. So really, any deep GP work that I think is out there has to take one of these things from the left column and one of these things from the right column and combine them in order to accomplish, just fitting the model. So like I said, questions are, well, which is better? Which combinations are better? Which are faster? And how do all of these things work? Should there be, reasons of which of these tools you should use when? So to test it, and we do have more information in our written discussion if you're interested, but we just did a sim study because I think that's how everything should start. So this looks like a lot, but we just took existing codes that were out there. So on the bottom axis, you can see each of these deep GP models. These are each a different way of fitting a deep GP model. And they all took something from the left column, so variational inference, HMC or ESS, and combined it with something from the right column. And there were 2 implementations that did variational inference and random features, which is what Sébastien cited as the Kudajar work, and then the kind of current work. And then we just did some simulations on a 2-dimensional example and a 6-dimensional example, different training data sizes, and looked at how well they did on just prediction error on a holdout testing set, and then continuous rank probability score. So lower is better in these cases. This was just a start to kind of see which may be better. Personally, I think Vecchia approximation is coming in as a really good idea. And I think this RFE is also coming in as a newer idea. And they maybe together maybe are going to uproot this inducing points kind of historically used method of inducing points. But there are also clearly other combinations that are at play here. Like there are coding choices at play. Some of these were coded in R. Specifically, my work with the slice sampling in Vecchia is in R. Others are in Python. Although our work performed better on all of these metrics, it's also the slowest. So there's trade-offs between how fast your computations are and what's more important to you, being faster or being more accurate. So I think this is an open area that warrants a lot more investigation and warrants a lot more work, and we're just scratching the surface. But that's all I wanted to kind of touch on for now.
All right, wonderful. Thanks, thanks very much, Annie. So we have some time, and thank you, by the way, for all sticking very well to sort of the timing, because this has been it's been very well you know, very well timed all. We have some time for a rejoinder. I think Maurizio is going to do that. There we go. So go ahead, Maurizio.
All right, let me unmute. Can you hear me?
Yep, thank you.
All right. So, I want to start by thanking Mark, as the editor of Bayesian Analysis, for giving us this unique opportunity to reflect on, you know, what we did some time ago now in our work. And I want to thank the panelists for their discussion. It's been really great to hear the criticism on some of the things, on some of the choices that we made. And also, I think Professor Higdon touches upon a really important point about how to actually use this in practice, you know, for real applications. We really offer something new here that was not possible to do before, right? And I kind of agree with the position of having to think a lot more about the statistics sometimes and less about the computations. So in my rejoinder, I want to discuss two main points that were raised in various places in the discussions. And one is the model approximation and inference, which Annie touched upon already. And another one is how to specify sensible priors with our deep Gaussian processes over the discrepancy, which is exactly what Professor Higdon was mentioning before. So for this presentation, I'll turn deep Gaussian processes into Bayesian neural networks. We saw that with random feature approximation, we can actually do that. And just for simplicity, I'm going to call all these weights in the intermediate layers as W. And so we chose to actually do variational inference because we could come up with an evidence lower bound, which is actually easy to optimize with stochastic optimization. We can actually mini batch all this. And by mini batching, I mean that we can actually we can optimize this Q of W to actually maximize this evidence lower bound. And we can actually optimize this by just providing mini batches of data. So this scales really nicely for various architectures and various sizes of the data. This was proposed by Grace in 2011. And unfortunately, in the last after we submitted this work to Bayesian analysis, we started working a lot more on variational inference for general Bayesian neural networks, for example, convolutional neural networks. And we started struggling with this because this is one of the questions also that I tried to answer in the question and answer in the chat before. So if you imagine that you have a model with 100 million parameters, which is kind of the norm these days, these people working in deep learning, they use these models with a huge number of parameters. This regularization term here, which measures the distance between your approximate distribution Q and your prior P, is going to have 100 million terms. Whereas this guy here is just the log likelihood. So if the likelihood factorizes, this is just going to be a sum of terms. And this is going to be an expectation under Q of a sum of terms, which scales as the number of observations. So if we have only a few thousand observations and a model with millions of parameters, this term here is going to dominate. And actually, variational inference, the optimization is going to push the posterior, approximate posterior Q to the prior. And so this over-regularization is really problematic. And maybe it's not the best way to approach these kind of problems for this kind of models with a lot of parameters. So here I just have a short video to illustrate what happens in logistic regression when you have a variational approximation. This is just to add some videos to what Sébastien presented before and how the optimization really tries to optimize this distribution, which is a fully Gaussian, multivariate Gaussian with a full covariance, to the posterior, which is this dashed line here. And you see that at the end of the optimization, we obtain something that nicely classifies the two classes and somehow approximates the posterior of the Bayesian logistic regression problem. So, but another way to go about this problem now would be to do Markov chain Monte Carlo. And thankfully, I mean, already in 2014, there has been a lot of work on ways to utilize similar ideas in stochastic optimization to actually do Markov chain Monte Carlo. So I reference here Chen and others, ICML 2014, but also Max Welling and EYT did some fantastic work on stochastic gradient Langevin dynamics. And this in particular is a stochastic gradient Hamiltonian Monte Carlo, which Annie also mentioned before. And this is pretty easy to actually implement. And we had pretty good success actually in implementing this recently and making it work for really large data sets and really large architectures, and even convolutional neural networks, so pretty well. And the idea again is that because the likelihood usually factorizes across observations, so this log likelihood is going to be a sum of terms. Then we have the log of the prior, and so this is again mini batchable in the sense that we can sample a number of observations randomly, and this is going to give us a way to estimate unbiasedly gradients of this log likelihood plus log prior. So we can effectively then use this within these algorithms that explore the space of parameters using stochastic gradients. And so here I have another short video on how this actually works. So we have here 3 chains that simulate this Hamiltonian dynamics where the gradients now are estimated in a noisy fashion. So this is all these gradients are somehow unbiased but noisy, right? So, and by running this Markov chain for long enough, we should be able to obtain samples from the posterior distribution. And so now with this short introduction to these methods, I just wanted to say that today, variational inference and stochastic Hamiltonian Monte Carlo, stochastic gradient Hamiltonian Monte Carlo, they have the same computational complexity. Each iteration is going to cost you as much as evaluating the log like a batch of data, right? So maybe MCMC, you have to run it for a little longer, but today, my position at least is that we should not exclude the Markov chain Monte Carlo from the outset. And if we really care about uncertainties, maybe we should invest the time to run this Markov chain for long enough to obtain sensible uncertainties. I also, maybe to complement what Annie was saying, was talking about before, so there is this whole community working on inducing methods instead of random feature approximation for Gaussian processes. Like a very fundamental work in that space is done by Michalis Titsias in IStats 2009. And so this formulation is using what's called the Nystrom approximation to Gaussian processes, a set of inducing variables that allows us to express the distribution over the whole Gaussian process. And this formulation is very clever way of defining a variational objective, which somehow works together with the approximation. So it's a very nice way of marrying with the variational approximation within this sparse Gaussian process approximation. So there has been a lot of stuff that happened after that. So we did a Markov chain Monte Carlo for sparse Gaussian processes. So I was kind of involved in this kind of developments as well. This is also some work that is quite relevant here. So we're stochastic gradient HMC for deep Gaussian processes approximated with these inducing points. And also recently we did something where we take it to the next level and we do Markov chain Monte Carlo of every possible parameter in this approximation. And this is AStats this year. So if you're interested in that kind of stream of works, you know, these probably are good references to look at. Now I want to spend a bit of time talking about the deep Gaussian process prior over the discrepancy and how we can actually do something sensible there. So why do we like Gaussian processes? Well, we like Gaussian processes because we know how to determine, how to specify functional priors that make sense. So by looking at, by just, if we think about this Gaussian process with the squared exponential covariance, So we have two parameters here that control the behavior of the functions that we can draw from these Gaussian processes. We have this length scale parameter that determines how wiggly these functions are, and also this marginal variance that allows us to control the marginal variance of the process at each input. So this is really like a fantastic way to specify prior. I would want to say interpretable, but people working in interpretability, machine learning will probably kill me if I say that. But it's quite a nice way to specify priors for these kind of models. Instead, for neural networks, the problem is that if we choose priors for each layer, each parameter in these models, it's really hard to understand what is the effect in the output. And here, what I'm showing you is that if we take this is a 4-layer Bayesian neural network. If we just pick priors which are Gaussian with standard normal priors, these are the kind of functions that we represent in the output. So this is with a fixed Gaussian prior. Here we have fancier parameterization, which never mind for now. But you see that the kind of functions that we are modeling a priori are functions that look kind of pathological because they're all kind of flat. And maybe this is not really what we want. Maybe we have some kind of Gaussian process prior in mind that might do something useful for our data, right? And so what we worked on for some time now, we came up with this new work that appears in GMLR this year, is trying to tune the parameters, tune the prior over the parameters of this Bayesian neural network so that we can try to match what the Gaussian process prior looks like. And so here we did it for different kinds of parameterization. So here it's just we have a Bayesian neural network with Gaussian priors. These are hierarchical priors in the sense that we have Gaussian with the hyper prior on the variance. And here we have so-called normalizing flows for prior. So we have something that is able to optimally transport Gaussian measures into something which is more complicated over these parameters so that we try to match these Gaussian process prior. If we do that, so if we don't do that, if we use this pathological prior in a simple regression example, you see that we tend to be overconfident in our predictions, whereas if we start matching our priors so that our functional prior is good, then we obtain something which is more sensible and we try and somehow mimics what the behavior of the Gaussian process is. But now what we have is that potentially with this Bayesian neural network, with these deep Gaussian processes, we have models that are more flexible. So we try to at least impose functional priors that make sense, but then the model is so more complex because we have this composition of processes that allows us really to model things that can be really, really stationary and very complex. So the problem is that how do we actually do it? So we're trying here to match samples from a Bayesian neural network with the Gaussian process. The Gaussian process is a closed form, but the samples from the Bayesian neural network don't. So we don't know what kind of functions we represent with this Bayesian neural network. So, what the first thing one would be tempted to do is to minimize some sort of KL divergence between the two processes, but actually it turns out that there is an entropy term which is intractable because we don't know the form, again, of this distribution over the neural network. So what we do, we set up a Wasserstein objective to be able to actually do this matching. And so this is, I don't want to go maybe too much into the detail, maybe it's a bit too technical, so more details in the paper if you're interested. But this is something that is actually pretty tractable to do, fully sample based. So if you don't like Gaussian processes, you like something else that you want to sort of match with your Bayesian neural network deep Gaussian process, you can actually do as long as you can obtain samples from it. So this is how the optimization works. So this is my last video. And so here, maybe I'll just make it smaller. So the target Gaussian process prior is the one on the left, and here, as the optimization goes along, the samples from the Bayesian neural network start to look more and more like the Gaussian process prior. And this is done before we look at any data. And then with this prior, we then do our analysis. So the idea here would be that if we know how to specify a good prior for the discrepancy, it should be possible, at least computationally, we have solutions on how to actually match these with our deep Gaussian process. All right, so I want to conclude here again with some concluding remarks on what we tried to do back a few years ago now. I think the first version is 4 years old now, the first draft of this paper. So our idea was I was fascinated by this work by Kennedy and O'Hagan. I think it's a great piece of work, and I thought that my expertise in Gaussian processes could maybe be used in order to alleviate some of the computational problems of the use of Gaussian processes. And today, maybe I would do things differently. We have many ways of doing approximations of the posterior, model approximations, and so on. This is also touching upon on a point that was raised in Annie's discussion with Bob Gramacy on the zoo of code that is out there. So most papers these days have code that you can use to reproduce the results, but then sometimes they are in a certain environment. They don't offer maybe all the possible approximations you may want to try, and so on. So it's really hard to do comparisons, and I really think that the discussion of Annie and Bob was really good in actually, bringing this point up, and I think it's really important. And today, I would say that I would not exclude MCMC. In machine learning, a lot of people still believe that variational inference is super fast compared to MCMC. There is some truth to it, but definitely if you care about uncertainties and your code is expensive to run, you may afford to run MCMC in the end. And it's also very scalable and works really well. Flexibility is a really good thing. So being able to work with these deep Gaussian processes is really great. But of course, not necessarily deeper is better. And this ties in with nicely with the Dave Higdon's discussion before. Model selection is a very important thing. As far as I'm aware, nobody does model selection for Bayesian deep learning and for Bayesian deep neural networks, Bayesian deep Gaussian processes. And this is something we are actually working on today to be able to actually bring this. And the reason is that not many people do Markov chain Monte Carlo with these models because nobody could come up with good priors. And so this recent work really allows us to start exploring this space. And I think it's really important to do. So we can do really model selection to understand what is the optimal depth and all these kind of things. And also, so this was what I said before, that now we have ways to specify sensible priors for deep Gaussian processes, both for discrepancy and for the emulator. With this, I thank you again for your attention.
Thank you very much, Maurizio. That was very complete as a rejoinder. There are a couple of sort of questions into the Q&A section. In fact, there's one in the chat as well about functional data analysis, in particular for putting priors on the warping function. Is there any question that you or Sébastien feel compelled to reply to quickly?
I'm just reading quickly. Okay, thanks for the references. I see that someone pointed at some work that we should probably read. It's also in the Q&A. Asymptotic properties of this approach can be combined with any neural network. So the asymptotics, I think it's a really, really, really important point. So can we guarantee that in the case of an infinite number of data, we converge to the true parameters, for example? I think that would be a cool question to answer. And so I think this goes back maybe to the problem of identifiability of this model. So you can be flexible in changing the discrepancy and at the same time moving the parameters theta and obtaining the same likelihood. So probably there is an issue of identifiability there that we're not curing. Well, for sure, we're not curing with this way of operating. Then there is someone raising the point about, so for example, one thing that I'm currently investigating is, what about, so if you have a computer model that is actually performing simulations, can we not use these outputs of the simulations as a way to inform priors of these Bayesian neural network and then use data to actually then obtain posteriors over these parameters? So somehow combining, so having the computer model to be a sort of source of a prior for these deep models. And maybe come up with a way, with a framework to actually do inference over the parameters of the models, of the computer model through this. But it's not clear to me how to tie everything in at the moment. But maybe it's something interesting there to investigate. Sébastien, do you have anything that you've read?
Yeah, I mean, in the question, the last question is about the theoretical foundations. So it's not clear to me because there are different aspects. For example, is it about the random features or is it about the calibration framework? What do you think, Maurizio? Because the random features come, yeah, it's a well-known approximation, where we know that there's a convergence in distribution using yeah, it's Monte Carlo on the covariance spectrum. Yeah,
variational inference also is has quite some good.
And also variational inference has links with yeah.
By the way, I mean, if the posterior, so if the approximating, so if the family of approximating distributions contains the posterior,
yeah,
you're actually making the optimization is going to make the lower bound tight, so that the lower bound becomes the actual model evidence. So that's why these normalizing flows, this kind of advanced ways of parameterizing your posterior distribution, can really get you very close to the actual posterior.
Yeah. If the optimization, if the optimization is perfect and the true posterior is in the family, you find the true posterior. Yeah.
Then there have been also proposed. I think I answered one of the questions about this importance weighted variational inference. So you have ways to actually spend a bit more computations, but achieve lower bounds that are tighter than the normal lower bound that we use in variational inference. So this is still a very active research domain. So definitely there are still many things that are happening in this domain.
And don't hesitate to check the code. In the code, for example, there's some small example where you can see in one layer, in the case of a Bayesian linear model, that you actually find the true posterior. There is a comparison between the variational inference posterior, that you retrieve the true posterior by inverting the matrix.
Yeah.
Okay, I'm going out on a limb now because it's going towards the end of what we envisaged as sort of time for this. But if there's any participants that are that want to raise their hand and ask a question, I think we have a little bit of time for that. If not, maybe one of the discussants wants to sort of say something in addition to what's been said already. No pressure here, of course, because as I said, we've had a rather lively discussion already, and quite an interesting and helpful one, I think. Is there anyone out there that is? Let's see what's in the chat now. Okay, somebody. There is. Okay, so one of the earlier poses of questions says that it's about calibration in terms of, I think that's what the theoretical foundations were that were not necessarily clear to the poser of that question.
In that case, probably the original reference of Kennedy and Reagan, it's a great place to start because I think yeah, that explores that in quite.
Yeah, we have to confess we don't improve things with identifiability with this paper. We have to acknowledge this.
Yeah. Okay. Any of the participants want to either type something else or raise their hand and ask a question verbally? No. Any of the discussants has something else just left to say that they really want to get off their chest? No? Okay, wonderful. In which case we're nicely on time. And let me thank all the participants, certainly the people who presented, of course, the authors of the paper, and the discussants for really, really, insightful comments, and of course, congratulate the authors for a really nice paper that led to, I think, quite an interesting discussion here. And I'm sure we'll still, once that it's published, I mean, people will read it, and it will sort of spark off ideas, I think, and sort of discussions that people will have in future. So it's wonderful to have this. Thank you all very, very much. And lastly, thanks to all the participants for being here. We had quite a few of you. I think it was up to the 80s at one point. So it's really nice to see that people engage from all parts of the globe. Thank you very much, all of you. And until we meet again, either in one of these or hopefully actually in a sort of a venue in person, perhaps. So it's been a real pleasure. Thank you all very much. Bye-bye now.
Thank you, everybody.
Thank you.
Thanks. Bye-bye.
Bye-bye. See ya.
Bye.
Bye-bye.
Bye-bye.